Hey everyone, it's your host Russ Altman here from The Future of Everything. In October of 2025, chemical engineer Will Tarpeh was awarded a MacArthur Genius Grant in recognition for his pioneering work to turn wastewater into a source of valuable materials. Will envisions a future in which the concept of wastewater becomes obsolete thanks to advances in recycling. Well, a couple of years ago, I sat down to talk with him about his work, and I hope you'll take another listen today to learn more about the research Will is doing to transform the way we think about wastewater. Before we get started, another reminder to rate and review the show so that others can discover it and enjoy it. Most of us probably do not think about wastewater very much. The last time we think of it may be as we watch the water go down the drain of our kitchen or our bathroom sink, or perhaps when we press the flush on the toilet, done and gone. But we actually all know that it's not really done, that wastewater enters a pretty complex sewer system. The sewer system ideally goes to some waste treatment plant that processes the sewage. Many of us don't understand precisely what goes on there, but the general idea is it makes it safer for dispersal. Now, in the worst case, sometimes it may be just pumped into the ground. That might not be so bad, depending on what's in your waste. Or it could go into the ocean or a lake. It's not very pleasant to think about, but we're thinking about it today. What do we have in the wastewater? Let's take a quick inventory. Well, we know there's water. We know there's human waste, both urine and fecal matter. There's pharmaceuticals, both through the human waste, and also some people dump their medications, although you're not supposed to do that, into the toilet. There's food waste, and of course there's whatever other things we or local companies add to the waste water. So the question is this waste useless, or might it have some value? Now, of course, we could use the water. And in fact, if we could get it filtered and purified, we could do a lot of things with it. Now, I have to stop here and tell a little story or a little confession. So in the building where I work at Stanford University, in the toilet, right in front of the toilet in the men's room, there's a sign that says, "Warning, the water in these toilets is recycled." And I must say that I've never understood why they're warning me and what they think I might do if they were not to warn me. So maybe we'll learn the answer to that question today. But what about the other material in wastewater? Is there any value there? Well, Professor William Tarpeh is a professor of chemical engineering and civil and environmental engineering at Stanford University. He studies the chemistry of wastewater and ways to process it to extract, and here's the fun part, potentially valuable substances. So William, I have to start by asking you, what drew you to the study of wastewater, and what are the hidden treasures that we might not appreciate in our wastewater?
Absolutely. Happy to talk about wastewater and all the value that it contains. So to start with your second question, wastewater is something that I and my lab group and many others in our field view as something of a modern mine. And that's because it can be constantly mined for value. And it also, unlike other mines, it keeps growing. As long as there are people around generating waste, we kind of have the mine wherever we need it. Some of these hidden treasures are things like nitrogen, phosphorus, and potassium. So these are the same things that fertilizers are graded by, like NPK ratio, if you've ever seen a fertilizer.
Written on the actual fertilizer when you buy it. And that gives you a rating of the amount of each of those substances in the fertilizer.
Exactly, yeah. And so if you're a gardener or you've been on a farm, you'll see that NPK ratio. So our wastewater itself every wastewater has an NPK ratio as well. We can also recover things like metals. We've been thinking about lithium from wastewater for battery recycling, some of the pharmaceuticals you mentioned. In terms of how I got interested and why I started.
So we'll definitely come back to all of those because this sounds fascinating. But let's hear the origin story.
Yeah, the origin story of how I got interested in what happens when you flush the toilet. I think besides my just kind of morbid curiosity of wondering what happened, I got really interested when I was in high school and thinking about water and kind of the right to water that everyone on Earth should have. And this was in the heyday of the Millennium Development Goals that were developed from 2000 to 2015. And now we have the pleasure of working toward the Sustainable Development Goals, their successors. But one of the big ones in both of those agendas is clean water. And one of the things that I saw was lots of people interested in ways to make sure there were nice drinking wells and things like this all around the world, and that these were of high quality so that people didn't have to worry about the quality of their drinking water. And sort of the other side of the coin that people weren't seeing as much at that time, but now has become a real part of the conversation, is sanitation. If you give people, or people have access to clean water, but don't have access to clean places for their waste, then arguably they no longer have access to clean water.
Right, because those systems can intersect and cross-contaminate.
Absolutely, in so many ways, whether it's pipes that are broken or are decaying, or lots of different ways for those to become actually one system, or they are always one system. And so that got me interested in sanitation. And then I when I was an undergrad, I learned that people studied sanitation for their whole life. And I thought I could be one of those people. And I just thought that was so exciting. And I love chemistry. And so the chemistry of wastewater just really emerged as the confluence of all of my passions.
It is actually quite remarkable that you were able to develop a passion as a teenager and actually see that through. You know, there's so many distractions, so many things that can change your interests. Have there been, just out of curiosity, major detours, or have you really been like one of the lucky few who can kind of stay on the track, and now you're a professor of chemical engineering working on exactly what you were hoping to work on?
Yeah, I think there were many detours, but one of the interesting things about what I do in water and sanitation is that we need so many different disciplines and expertises at the table on this issue. From, you could think about user design for toilets to artificial intelligence for monitoring toilets and when they should be emptied and that type of thing, all the way to the chemistry of what I do now. So even the detours I took, right? I minored in African studies. I studied abroad in Cape Town. I did all these other things. I love teaching, right? But all of that came down to, like, I could still, no matter what detour I was on, so to speak, what path I was on, I could always come back to this thing I was really passionate about, but just from different angles.
So I know we're going to get into a great discussion about the applications of your work, but can you give us a little sense before we leave it of the technical, what's the core technical capability that you as a chemical engineer bring to this problem for the removal of all of these substances that you gave us a little teaser for a few minutes ago?
Right. Yeah. The core of what we do is, we call it selective separation. So you could also just think of it as really selective extraction. Another way to think about it is, you may have heard the term circular economy, right? Making sure we're closing the loop on all types of things. And so you could think of a general circular economy, like around the whole world or whole industrial ecology altogether. You could also think about this from an element specific point of view. We could make a circular nitrogen economy or circular lithium economy. And so being a chemical engineer, what I focus on is, how do you take a wastewater that has dozens, hundreds of different chemical compounds in it and just go after one, right? And so we design materials like membranes or resin beads. If you've ever opened up like a Brita filter, those types of beads, we design those at the molecular level. We also design, in addition to those materials, we design processes using electrochemistry. So to be like crude about it, you could kind of hook up a car battery to water and get certain ions to move faster than others.
Because some of them are positively charged, some are negatively charged, and so that's a separation technique.
Exactly. And so that's what we're after. But everything we do, whether it's for nitrogen, lithium, potassium, phosphorus, we have all these different resource recovery cases, we call them, but it boils down to three things. What element are you after? What wastewater are you doing it in? And what product do you want to make? And when I say product, I mean, do we want to make a fertilizer? Do we want to make an acid or base or commodity chemical that consumers won't see, but our chemical industry depends on?
Great. Okay. So that gives us a really nice idea of what the fundamental technologies are. And let's go now to the value. And so the first thing you pointed to as valuable is this nitrogen. I think was it nitrogen, phosphate, and potassium? Yes. NPK. And this is used in fertilizer. So do we have significant amounts of that in our wastewater? Where does it come from? And is it going to ever be economically viable? Will this pay for the entire operation because of the value of what you're being able to extract from this wastewater?
Right. Yeah. So we do generate, as just humans, as we excrete naturally, we generate a fair amount of nitrogen, phosphorus, and potassium. So one kind of back of the envelope that we've done in our lab is, say you collected, we study urine a lot. So say you collected everyone's urine, like all 7.8 billion people's urine.
Okay.
And you extracted all the nitrogen out of that urine, right? We're of course making simplifications here. What percentage of the global fertilizer demand could you satisfy? The number is somewhere between 20 and 30%, depending on your assumptions, right? Which is nothing to, I mean, that's not 100%, and we didn't expect it to be 100%, but it's also not 2%, right? It's fairly considerable. And so when we think about environmental impacts and how fertilizer is produced, offsetting 20 to 30% of the nitrogen production, I mean, nitrogen fertilizer production is the most energy intensive chemical manufacturing process. So there's some gains to be had there.
So that's really interesting, because I think a lot of people might think that the body has extracted everything of value. You know, we have this idea that everything of value has been extracted, and what we're putting out at the end is really not very valuable or useful for anything. But at least for those three elements, we're putting out kind of high value chemicals and you point out, of course, we're probably not going to harvest 100% of human urine. On the other hand, there's probably other sources of nitrogen, phosphorus, and potassium that are also adding into the water system that you could also reclaim. So it's almost an anti-pollution. Is that fair to say? Right. An anti-pollution or a mitigation strategy?
Right. Yeah. So we have two value propositions or motivations here. One is to prevent the pollution, right, of nitrogen and the pollution consequences of nitrogen, phosphorus, potassium, some of these other elements. The other is to make valuable products and kind of reduce the environmental impacts of chemical manufacturing. And so between both of those, we feel like being right at the nexus, we can achieve both goals and do so in a more efficient way.
This is the future of everything. I'm Russ Altman. I'm speaking with Professor William Tarpeh about urine and all the good stuff you can get from it. Okay, so that's great. So the fertilizer thing is a big deal. What about other things that we should be monitoring in the urine? I know that, for example, I think you mentioned, and I mentioned in my intro, that there might be pharmaceuticals floating around. What are the challenges for pharmaceuticals in the urine or opportunities?
Yeah, one of the challenges we hear when I was a postdoc at University of Michigan, our broader team did some surveys of people and said, okay, what are the big obstacles you see to urine-derived fertilizers, and/or would you eat a crop fertilized with urine or some
crop? That's crop with an O.
Yes, yeah. Would you eat a crop? Would you eat a plant that had been fertilized with urine or a urine-derived fertilizer? And a question that kept coming up was, what about the pharmaceuticals in urine? And this was from kind of the general public, and we were really pleased to hear this, because this was the same thing we were thinking about in the lab. The short answer is that urine does contain a fair number of pharmaceuticals, and these pharmaceuticals in wastewater treatment plants, we tend to remove them through chemical processes most of the time. And if we don't do it well, it can cause ecosystem effects, right? You may have heard of changing gender dynamics in fish populations, for example, due to pharmaceuticals and estrogen. But one of the things that we can do is, and so when we're trying to make a nitrogen fertilizer, we want to make sure it's pharmaceutical free, right? And so in the separation techniques that I design, we try to do that, get the nitrogen and leave the pharmaceuticals. Kind of the next iteration of this, when I think of like, what's the crazy future of maybe even the current.
We're all about the crazy future here on the Future of Everything.
Yeah, what I'm wondering is could we actually recover pharmaceuticals from wastewater, right? So this is kind of the closet pipe dream I have.
Pipe dream.
Somewhat pun intended, right? And the dream here is that by the same logic that we take a nitrogen pollutant and convert it into a product, could we do that for pharmaceuticals themselves? And of course, right, there are social and technical issues that we need to think about. Would you want to drink water would you want to take a drug that had been in someone else's body? Those are things that we need to think about. And it's not something we should do tomorrow.
But if it's an incredibly expensive drug, which is limiting treatment of patients globally, that argument could be pretty compelling.
Right. Or could we get like just the active ingredient back, right? Or the most expensive component back? Or one of the things I love about wastewater, and that I think is also in the future of wastewater, is broadening the definition of wastewater, right? Wastewater, of course, is, as you mentioned, what happens in our sewers, but wastewater is also produced at a pharmaceutical plant, right? Could we just do it right at where the pharmaceutical is produced and what they accept as a lower yield, lower than 100% yield? Could we recycle that, put a unit process in that gets us some of the active pharmaceuticals?
So I'm really glad, because I wanted to make sure I got to this issue of infrastructure. So as you know, better than me, right now, all of the waste products go into pipes that get bigger and bigger and bigger, and they go to a big sewage system. I've heard that there might be other models for how this might happen. So can you paint for me what the opportunities are for moving away from the bigger and bigger pipes, leading to a huge pool of mixed? Are we looking at a different infrastructure in the future?
Yeah, absolutely. So in some ways, the future of wastewater we talk about in my field may be decentralized, right? Better put, it may be kind of flexible scale, or there may be a spectrum of scales. Right now, the majority of infrastructure that's associated with wastewater is these pipes that get bigger and bigger and end up at a treatment plant that's on some body of water.
Right.
And this, the thing about this is that it's definitely a great solution if your problem is pollution and pollution alone. But if your problem now in the 21st century is pollution, scarcity, environmental impacts, energy, cost, now with this multi-criteria problem, the centralized one is no longer a one-size-fits-all approach. And so what I mean by that is that even if we tried to do centralized infrastructure around the world, by 2050 at current proliferation rates, half of the people in Africa and Asia still wouldn't have access to sanitation. Many of us consider that unacceptable.
Right.
And so to fill that gap, we need to have flexible scale approaches.
Tell me what decentralized looks like. So I get the idea that we're not going to have the big sewers treatment plants. What might we have instead?
Yeah, you might have a neighborhood scale treatment plant, right? Or you might have a household scale treatment plant, a point of generation treatment plant. You may have heard of point of use water treatment filters, for example, right? Like you open the cooler at the office and there's an activated carbon resin right there, or activated carbon cartridge right there. Same thing, but for wastewater, right where the wastewater is generated at the toilet level. That's like micro centralization, right?
Right.
That could be an option. And this has some benefits. Another example is like septic tanks, right? Like lots of people in the US, up to a quarter of our population is actually not on centralized sewerage infrastructure.
Right.
And so there are different challenges, but also different opportunities, right? You can have more.
So in a way, they're pioneers for these decentralized. But this will be a new generation of decentralization where, the kinds of devices that you and others are designing will be scaled down and made so that they can effectively work on a household or a block scale. Absolutely. What about the idea of having the effluents separated? So one of the things that always strikes me is my kitchen waste, my toilet waste, all of it goes into the same pipe. So there's already a pretty big pipe coming out of my house. Is there an argument for having separate pipes with different kinds of waste leaving the house going into this decentralized system? Does that make sense?
Absolutely, yeah. And so the term we use for this is called source separation, right? Which just means separating the wastewaters where they're at the source, where they're generated. And this may sound like a crazy idea, right? Having multiple pipes in your home. But then let's think about solid recycling, right? In solid recycling, we already do source separation in some cases, right? We separate glass from plastics from paper. Right? Think about the same thing, just their water streams.
Yes, every week I have a ritual to separate my recycling. It's very important to me.
Absolutely. And it's something that we just all learn to do, right? Humans are very adaptable. By the same token, you could imagine having a pipe in your house for food waste, a pipe for urine, a pipe for feces. Hopefully not that you have to separate yourself, right? But separating them at the source helps us do the recycling better, right? When you have cross-contamination, you have paper in the plastics recycling, it makes it harder to recover plastics from plastics. Same logic.
So, and it strikes me that if you did do that, some of it might be hyper-local because you know how to deal with it, but others maybe you aggregate at the block level or at the city level because you just need a certain amount of volume for the efficiency of your different systems.
Absolutely, yeah. And so that flexible scale comes right in there. Like you said, Russ, you could have the urine could be treated at the household, but maybe the fecal matter goes to the whole city level, right? And that gives you a lot of flexibility to put everything, each treatment operation, at the scale at which it's most efficient.
This is The Future of Everything. I'm Russ Altman. More with our guest, Professor William Tarpeh, about urine, wastewater, and a lot of issues that I really want to get to next. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Professor William Tarpeh about urine, wastewater, the hidden treasures. And now I wanted to move to something you actually made reference to the less resourced and developing world and your interest in Africa. And I wanted to ask, what are the opportunities? What's the problem and challenges facing those communities? And how can some of these technologies improve living conditions?
Absolutely. The problem is quite sobering. So over 4 billion people don't have access to collection of their excreta and treatment of their excreta, right? And this is hard to imagine for people in the US because we just literally flush and forget.
And so that's more than half of the human population.
Right. And sanitation is a really central thing. It affects everything from taking extra days off work because of extra diarrheal disease burden, all the way to girls staying home from school when they reach menstruation age and don't have access to private toilet facilities. And so it has really far-reaching impacts. The good news about this is that there's a ton of energy happening on the sub-Saharan African continent and in Southeast Asia as well. on ways to close this gap and actually do some leapfrogging, as we say in the development engineering space, to get from where behind, so to speak, industrialized communities to ahead of industrialized communities. And what I mean by that is that we don't have, when we're doing work in Kenya and in Senegal, we don't have the sunk cost in centralized treatment plants as much as we do here in the US. And that means there's some flexibility, of course, to do things responsibly, but there's also flexibility here to collect urine and feces at different scales and leapfrog and do some new treatment and new collection that frankly we can't do at scale.
So this is very similar to like the cell phone situation where some of those communities never had to build telephone poles because they could jump directly to cell phone infrastructure with the towers. And now we're saying there's a great, you're getting very excited because a lot of the technologies that you're developing might be the first technology that gets deployed and not any sense a replacement of an older system.
Correct. And in some ways, it might even be like the first implementation of some of our technologies might be in Nairobi or Dakar, not in San Francisco, which I think is quite
which could be very satisfying. So tell me the experiments that are ongoing or planned or whatever the status is.
Yeah, so actually right before the pandemic hit, or we were all aware of it in December, I took a team of students to Dakar, Senegal, and there we were meeting with one of our partners, Delvic Sanitation Initiatives. And they run these, they call them fecal sludge treatment plants because they're more concentrated than wastewater treatment plants. And they're all about resource recovery, recovering valuable products from wastewater. And so they've managed to make briquettes, and there are all these different things you can make from feces and from urine. Most of the time, our partners are able to take care of the feces, but they're kind of left with the urine that they separated out so that they could dry out the feces. Right. But they're like, what can we really make with this urine? And that's where we come along and say, you've got urine, we've got solutions. And so we come and say, well, we can make nitrogen fertilizer, we can make phosphorus fertilizer. One of the things I'm really excited about is we've managed to not just make acidic nitrogen fertilizer, but we can also make alkaline or basic nitrogen solutions that can be disinfectants. They can be used for all types of different chemical manufacturing processes. So we call this expanding the portfolio, right? Yes. To expand a product portfolio. Conventional business wisdom says a diverse portfolio is a stronger one. So
right. And so it strikes me that one of the benefits may be that these things are being produced right where they may be needed. So transportation costs, sustainability goes up. I mean, is that true?
Absolutely. Yeah. So what we see, we did a study in Kenya a few years ago where we saw that the cost of producing fertilizer from urine was actually lower than the cost of commercial fertilizers in Kenya. And some of that has to do with transport. Like you mentioned, most fertilizer there is imported from actually India or China. And also the value proposition there was not so much that it was urine derived and that it was this green thing, which are cool things about it, but it was that it was locally sourced, right? And so having locally sourced fertilizer was a huge value add for a place that has limited fertilizer access. Fertilizer access is lower than it would be otherwise.
I'm also struck that when, and you were mentioning business principles, your supply chain is pretty robust as long as there's no big disease or terrible problems with health. Your population stability then translates to stability of your basic ingredients for then going ahead and doing these transformations.
Correct. Yeah, because we can do it, like you mentioned, right where the people are. And so this brings up some issues in terms of like transporting to agriculture, which is why we've turned to some non-agricultural based products.
Yes.
And especially in sub-Saharan Africa, when we think about population growth, the majority of it is expected to happen in developing country urban centers, right? And that's where population growth is outpacing infrastructure. And so what we're saying is we can deploy these strategies where that problem is most stark.
Right. And then now I can start to see where your sense of urgency would come from, because these are dynamics that are happening today. This is not a future state. A couple of things I know you've written about. I just wanted to touch base on algal blooms. Right. So how does your work, that was a surprising thing to me, that your work would be related to these things that happen in the ocean. Can you connect those dots for me?
Absolutely, yeah. So to connect the dots, I'm going to double down on the pipe analogy here, but we're just moving down the pipe that goes into the environment, right? At first, we were right at the point of generation. Now we're at the point of discharge into the environment. At the end of that pipe, if you can imagine an ocean outfall pipe that goes out 2 miles, like some of our plants do here in the Bay Area, what we're doing is emitting nitrogen and phosphorus into the ocean, right? And conventional not-so-wisdom would say, dilution is the solution to pollution, right? But in reality, what that does...
That's a good one.
but in reality, that dilution, so to speak, leads to these it overfeeds algae, right? We're giving them more nutrients than they would have otherwise.
They like the nitrogen, and that's what causes the bloom.
Exactly. So harmful algal blooms come up, and what happens there is that those threaten aquatic ecosystems. They can overconsume oxygen. They also threaten public health, right? So in the Great Lakes of the US, we see these algal blooms like in Lake Erie every year that actually produce cyanotoxins that can harm drinking water. But most of our work is focused on the Gulf of Mexico, where these dead zones, oxygen poor zones, can arise every year that are the size of New Jersey. And so we've started thinking about, okay, we've got to be able to do better than this, than just watch an algal bloom happen every year. And so we've actually miniaturized some of our treatment devices and turned them into sensors so that we can predict and sense when that's going to happen, and then say that's where we need to deploy the wastewater treatment. And so again, the benefit here is that we're flipping things on their head a bit. Most of the time we pump water to treatment site and the treatment site is fixed. What we're doing instead is bringing the treatment to the water through deployable sensors and deployable treatment devices. And so that allows us to capture the 80% of wastewater worldwide that's not even collected. All the other stuff I've talked about at its best can only address collected wastewater. This gets us the other majority that isn't collected.
So one of my favorite sayings in engineering is, in order to intervene, you have to be able to measure. And so what you've done is you've created these measurement devices that before the bloom happens can issue an alarm. And then you guys can focus your resources on the area that's about to have and you don't have to filter, literally, you don't have to boil the ocean. You can just boil or detoxify the piece of Gulf of Mexico, in this case, that is threatening to have a bloom.
Right. And that's the hope. And then some of the idea there is to bring that back actually to the up higher in the pipe, so to speak. And we can use those sensors to actually mine some of the data that's in wastewater. So we can also know what are the ammonia levels for a given community or for a given installation. And this can help with regulations as well, right? When we say that, like, you, industry X, can only emit this much nitrogen, how can we prove that they're only doing that? We could have a third-party sensor, right? Or government sponsored sensor campaign that actually.
So now we may be looking at nitrogen credits in addition to carbon credits.
Yeah, these are things that we're writing about in our field and thinking about. Are there nitrogen and phosphorus credits that should be issued in addition to carbon?
So we only have about a minute left, but I wanted to ask you about the Urine Summit. It turns out, I think, that's a real meeting. I don't know if that's the official name, but tell me about the Urine Summit and why we should be excited about this.
Yeah, the Urine Summit is our unofficial name for the Rich Earth Summit, sponsored by the Rich Earth Institute in Vermont. And it's where we get technology developers, policymakers, enthusiasts, horticulturalists, everyone who's interested in urine as a resource together every year. And this past, just a couple months ago, we had over 100 people interested, and there were lots of talks, some technical, some more policy focused. And it's where we're trying to move the needle on viewing urine as a resource and putting that into policy and into building codes.
It must be so exciting for you to find like-minded folks who are thinking about and who appreciate your work, but also are thinking about the same problems. Community is so important in science, and so that must be a great event. And I'm sure there was a lot of sadness about not being able to do it in person this year.
Yeah, I walk away every year thinking we've gotten closer to the future of what urine treatment and urine collection and urine valorization will look like.
And it sounds like you're bringing together both academia, industry, and government, and that's kind of the trifecta of all of the kind of stakeholders who can really move the needle when it comes to changing practice and getting us to the future.
Absolutely, that's the hope.
Thanks to you for listening to the Future of Everything podcast. We really appreciate it. Don't forget, we have now 300 back episodes, and so you can spend a ton of time listening to interesting conversations about the future of anything. You can connect with me on many social media platforms, including LinkedIn, Blue Sky, Threads, and Mastodon. I'm at RB Altman or at Russ B. Altman. You can also follow the Stanford School of Engineering at Stanford School of Engineering or at Stanford ENG.